Since one of the newer things this section is defining phi and theta for spherical coordinates, I thought it'd be good to look at some examples of how we define the angles for the region of integration using spherical coordinates. So I went online and clipped a few example pictures that we're going to look at, ranging from less complicated to more complicated. So for this first picture, let's just give it some numbers so it's less abstract to think about. Let's say this is, again, one of our ones with radius 2. So we've got our radius, starts at the origin, goes out to the furthest distance on the sphere. Distance on a sphere is always the same. It's the radius. So our rho is pretty straightforward. And then our theta, we define using our xy plane only. And we see how far we spin from the positive x-axis counterclockwise, just like we would have before. So just to be clear, kind of if you were looking at only the slice in the xy plane, it would look like this. And so hopefully you can see that that goes from theta equals 0 up to theta equals pi. And then our phi we define from the positive z-axis spinning down towards the xy plane. Somehow these arrows make it look less like a circle every time I add one, but I don't know a better way to do this. So that wedge shape that we're thinking about is the same as the wedge shape we had in the spherical example, and it's going to look like this. Oh, I know. If I use different colors, that'll make it better. Okay. Just bear with me for a second. Okay, so we changed our radius to 2. That one can be black. And then this shape right here, we said gave us theta, which is the same as this shape right here from 0 to pi. And now we're on to the phi slices. So we're thinking about the angle you span when you start from the positive z-axis and spin down towards the xy plane. That gives us phi. And so you can see that phi starts at 0 and goes down again to pi over 2. I hope those colors helped. And so if we needed to set up a region of integration over this over this quarter circle, quarter sphere, that has positive z values and positive y values, but x can be anything, these would be our bounds of integration. This is a quarter sphere. We lose half of it in theta. We don't have the back half of it below the x-axis with negative y. And then we lose another, quote, half of it, but really we're only cutting out a quarter because we've already cut out the back half when we cut out the bottom part where z is negative, and we stop at the xy plane. All right, so next up is this eighth of a sphere, and for some reason the picture chose to be oriented this way, so I'm just going to change it to be oriented like we orient things. So x, y, z. And we're going to go ahead and give it a random radius. We've been doing 2, so let's do 3. All right, so our radius is 0, less than or equal to rho, less than or equal to 3. You can have more complicated radius for spherical problems, but since the tricky part is these angles, I really wanted to practice that. So for defining our theta, we think about living in the xy plane. So I'm going to outline the shape in the xy plane. It looks like this quarter circle. When we think about theta starting from the positive x-axis and spinning counterclockwise, and I'll draw a picture again. Here's x, here's y, and here's the shape we've traced. So theta is going from 0 up to pi over 2. And then let's do the same with our phi angle. Phi is going to be concerned with this shape where we start from the positive z-axis instead and spin downwards. And it's also a quarter circle shape that looks like this. And it's the same as the example we looked at before, actually. So we know that that phi starts at 0, it lives on the z-axis, and then it goes down until it hits the xy plane. That's up to angle pi over 2. Right, this described an eighth of a circle. So what we're doing is when we take theta from 0 to pi over 2, we're throwing away like 3/4 of the sphere. We're throwing away this part of it and then this whole back half of it. And so we would be left with 75% of a sphere. So we would be left with a quarter of it. And then we cut that quarter in half because we throw away the bottom half of phi. Phi could go down to here, and then we would have a quarter sphere again, just like this one. But now we only have an eighth. So that's that shape. And then this is where it starts to get a little bit more complicated. So I think these came from like the Wikipedia on how to compute volumes and stuff. That's why it gives you a lot of values. But here's our coordinate system. And we're going to say that we're thinking about this blue region as what we want to describe. Blue being the one I just shaded in if those colors look the same to you. And then ignore all these letters. What we really care about is we're going to give ourselves a radius, and I'm going to go wild. I'm going to say that's radius 18, just for fun. So since we start at the origin and go all the way out to the edge of the sphere, we know that the radius of the sphere gives our upper limit for rho, and we start from 0 because the closest distance we ever are from the origin is the origin. Okay, and now we want to think about our thetas. So before it was a little bit easier because our shape did live somewhere in the xy plane. So we really have to think about projecting our shape down into the xy plane. You know, that idea of casting a shadow that we learned about. So if we're looking at this cone shape in the xy plane, it looks like this circle. And so our theta is going to start from the positive x-axis and go as far as it has to span that entire circle. And so that happens to be going from 0 to 2 pi. I'll sketch that, I guess. It's that slightly skinnier circle than an actual cross-section of the sphere because we cut it here. Maybe this will make it clear what I'm doing. Hopefully you can tell that what I'm saying is I'm looking down in the xy plane at the shape that cone makes, and it's a circle. And since we're covering the whole circle, theta has to go from 0 to 2 pi. And so next up, we have to think about phi. So phi depends on starting from the positive z-axis and then tracing out our shape going downwards. So since our shape doesn't hit the xy plane, we know that we're not going to have that same upper limit, phi going to pi over 2. But we do still start at the positive z-axis, so we know that the lower bound for phi is 0. And the upper bound is right here. And I'm just going to go ahead and say that that's exactly halfway down to the xy plane because it looks pretty symmetrical. So I'm going to say that's pi over 4. And I'll draw a picture of what I'm looking at here. Here's z, here's x, and I drew this cutout for us. And so we're saying that this angle right here is pi over 4. This right here is the same shape I drew right here. So that's how you would get those angles for phi of kind of like a cone shape in a sphere. So there's a word for that, I'm sure. You can think about it like an ice cream cone that's been cut out of a sphere. And, you know, just for fun, actually, that one's the blue cone that I'll denote with a star. But if we wanted to actually look at the red part that's left over, our radius is the same. The fact that we spin all the way around the x-axis, so the sphere covers from 0 to 2 pi stays the same. And all that changes is phi. The leftover red part that I'll denote with like that flower shape again, we're actually just going to say, okay, now our phi started here and it goes all the way down to the negative z-axis right here. And so that means that we start with our phi, I guess I should be consistent. I'll use like a tan color for it's not quite the same as what we were doing before, but still the same variable. Okay. So now our phi starts back here where our other one ended and then spins all the way down. So it starts at pi over 4 and it ends at pi. So that's how you would describe that other shape that's kind of like a circle that you cut a big cone out of. I don't know, like you're cutting a piece of fruit in a really weird way, might be how you create that shape. Okay. And then 4 is this shape right here. I couldn't find a picture that's on a graph like this one that keeps it all together, but we're going to be thinking about this shape right here. And so we'll just say that this is our z-axis, and then we'll put our x-axis there and our y-axis there. And what we've done is we've taken a whole circle shape, sphere shape, and we've cut out a little wedge of it, kind of like the section of an orange would be what this shape is. And again, we will give ourselves a random radius. I'll go back to 2 because 18 was just too wild. So rho starts at 0 because we reach all the way to the origin and goes out to 2. And then we got to think about our theta being the part of our sphere in the xy plane or projected down into it. And so that's shaping out this, which is really hard to read on the purple blue. So let me change my colors. Didn't think about that. Okay. So I tried to draw it where it is starting at the x-axis and then it spins out this little wedge. And so what I'm looking at is here's y, here's x, and this is kind of the shape that I've drawn right there. So if you've ever eaten an orange, this would be kind of like you're looking down the top of the segment. It has that little triangular shape. And so our theta, when we look at this picture, starts at 0. Let's say that's not all the way to halfway. Let's say that's pi over 3. And then our phi, we're going to get by starting from the positive z-axis. So that's up here. And then spinning all the way down to the negative z-axis. So that's right here. That's the like smiley face shape of an orange wedge. And so what I'm looking at is here's z, oops, going all the way down. Here's x, and then the shape we've traced out is like this. And so our theta starts at 0, positive z-axis is covered, and then goes all the way down to its lower limit of pi. Same way this one reached all the way down to the negative z-axis, so its upper limit was pi. This one has upper limit pi, but phi started from 0. And then if you wanted to cover this area that I didn't include in the graph, then it would be kind of the same approach as before, except for the way we cut out this little slice was using theta. So the rest of this shape starts from theta equals pi over 3 and goes up to theta equal 2 pi. Yeah, so those are some examples. Not every shape possible, but hopefully get you thinking about these types of angles.